So that's what I was thinking too, but it sounds kind of normal. But it's, I think, actually just simply the internet connection. Yeah, I think it's just simply the bit rate or whatever. Yeah. Oh man. Okay. Hopefully this stays. I have the headphones on so I can hear what it sounds like. Um, Actually, it's super annoying because I hear the what I say a few seconds after I say it. So I'm going to take them off. So if the audio starts sounding really terrible again, let me know, please. The video looks really bad. Is the video look really bad for you guys too, or is it just me? The video looks really bad. Is the video look really bad for you guys too, or is it just me? Okay, that's good to know. I guess it's just like on my end, looking at the thing, it just looks really blurry. Awesome. Okay. So disregard all this stuff right here that I wrote. I only got one email for a question for today, and um, one of the questions was, is there any way to quantify the number of antibonding electrons in a mixed orbital? So the way that I would approach it and think about it is essentially, right, for the right, because and I think where this comes from, right, is when we were talking about NH3 or anything like that, where we have the combination that was like this, right, and so then we have this guy right here, right, and then we also had this one right here, right, so this is the 1A1, 2A1, 3A1, and then we had the 1E and the 2E, right? And so I think the question comes from this right here. Since this is going to have essentially be a combination of the anti-bonding orbital, right, of this part right here, plus the bonding orbital, right, of this combination right here. And so the way that you wouldn't necessarily think of the electrons per se as contributing towards specifically an anti-bonding or a bonding combination, but what you can kind of think of it as is that the electron, right, that you know, and so if we fill in, right, because it's right, so this is the 3 hydrogens, this is the nitrogen, and then we have this right here, right, and so that's right, and so this part right here is going to have then the anti-bonding character, right, so this is going to be the sigma anti-bonding for that, sigma bonding for that, this is sigma bonding. You can kind of think that this right here cancels out that initial one, right, but then you still have the bonding character here, so that way you're still having 3 full bonds, so to say, between the nitrogen and then the individual hydrogens in this instance, right? You wouldn't consider them to be completely separate and stretched out. Let me update the Canvas site real quick, just because I think a lot of people may have difficulty trying to find this one. But does that make sense for everyone? Slash, do you guys have any questions? Question, for MO diagram of NH3, we showed in class that the reducible rep was A1 plus E, and that all makes sense. However, when I looked online at tutorials, they also had 2A1 plus 2E for the nitrogen atom for a total of 3A1 plus 3 for the entire NH3 molecule. That doesn't make sense to me, just because, I mean, I would be fine with it having a second A1, just because right then it would be the 1s orbital on the nitrogen, but even then, right, that's going to be so low in energy that it's not going to actually matter. But the second E, I don't know where that one would come from. Right, so in our case, right, we have 3 A1s, and then we have only 2 E's, but I don't know where the second one. For example, the 2s orbital for N is A1, the 2px is E, 2py is E. Ah, okay. Now I understand what you mean. So, E is one of the 2d orbitals, right? It's one of the doubly degenerate ones. And so the 2px and the 2py are 2E orbitals, right? But they're degenerate. They're always come together as a set. They're never separate. So in this case right here, right, we have these listed as the 1e orbitals, right? But it's 2 orbitals that you have right here. So E is always going to be 2 orbitals that come together, right? So you have essentially, right, if you have the pz here, right, that's going to be A1, right? And then you have your px and your py. But those together are going to have E symmetry, right? Because they're always going to come as a set, as a pair. They're never going to be considered from one another, right? They're always going to come together. And so, right, so what you would have is essentially those two right there. And then in this case right here, right, you're going to have an A1 plus an E. And then in this case for the 1s, right, this is going to be A1. So that makes sense in that case, right? But this E, right, if you were to draw out the different combinations, right? So for the hydrogens, right, the different salx that you can have, right, is the one combination that looks like this. So this has A1 symmetry. Then you can have the combination that looks like this. And then you can also have a combination that looks like this right here. Both of these are degenerate, and they're the E, and they have E symmetry, right, as a combination. Those two right there are always going to come as a pair in a C3V molecule that has, essentially this bonding pattern right here. And so that's why I think what they're doing is they're separating out the px and the py from each other, but they actually have to come together. So they're only going to be one single E. I mean, they're going to be two molecular orbitals. Both of them have E symmetry, but they're always going to come as a pair. So you would consider those to essentially be E orbitals in that case, right? So you would just simply call that like 1E, and then the antibonding combination would be the 2E. Does that make sense? Right? Just like it, right? And so then if we like do the thing, just to draw out. Oh. So I think that's where they were essentially coming up with the idea of the 3 A1s and the 3 Es in total for NH3. Because like if they're going to use that reasoning too, it wouldn't be 3 A1s and 3 Es, right? It should be 3 A1s and 4 Es, because you have two different salx, right, that you're going to have for that have the E symmetry, right, that have to come together as a pair. You can't separate them out. Does that make sense, Sharon? Right, so just to be like 2s, and this is the 2pz, right, and then this is the 2px, and the 2py. Yep. You guys have any other questions, or? No other questions or anything? Is bond length directly proportional to bond order? Yes. So, or is it direct? I think it's indirect, right? So, the shorter the bond length, the higher the bond order, right? So, if you have a triple bond, the bond length is going to be shorter, right? So, a carbon-carbon single bond is longer than a carbon-carbon triple bond. From the NH3 example, I am a bit confused how we got from calculating 1 for Na1 and Ne to actually drawing the MO diagram. Okay, so, right, so when we're thinking, so right, when we would draw the diatomic NO diagrams, the way that we would always approach it, right, is thinking about those three rules. We have to have the atoms, right, they have to be the distance away from each other that allows them, right, to form bonds. The orbitals have to be energetically close enough for them to form molecular orbitals, right, so around 15 electron volts. And then the last thing is that they have to have the right symmetry, right? So you can't have a 1s orbital forming an molecular orbital together with a p orbital, right? That's perpendicular to it, because they don't have the right symmetry in that case. And so what doing the whole reducible representation thing does is it lets us know what the symmetries are of the different combinations of the atomic orbitals on the atoms surrounding the central atom, right? So we have these different combinations that can exist, right? They're all unique. They're not the same in these cases. And so what that does is going through doing that whole process tells us what the symmetries are of these different atomic orbital combinations. And so by knowing what those symmetries are, what we can then do is look at what are the symmetries of the atomic orbitals on that central atom, right? So we can see, right, that for that central atom in a C3V point group, the s orbitals are going to have A1 symmetry, the pz orbitals are going to have A1 symmetry, and then the px and the py orbitals are going to combine together to have E symmetry in that case. And so all we're doing now is seeing, okay, right, we have these orbitals on the metal, or sorry, not on the metal, but on the central atom, right, on the nitrogen in this case. Which one of those match up with the symmetries of the atoms that are bound to it in that instance, right? And so we can see here, right, that the two different combinations that we can have of the atomic orbitals on the surrounding atoms is also A1 and E. So that just simply tells us, right, that there is going to be essentially the A1 combination from the surrounding atoms, right, from the hydrogen in this case, are going to then be able to form molecular orbitals with the pz orbital on the nitrogen and also the s orbital on the nitrogen, right? And so we're just basically then doing the same thing that we had done for the diatomics, where we're now forming, the sigma bonding orbitals. We're thinking about, do we have any type of orbital mixing where we have the anti-bonding combination from one set interacting with the bonding combination of a different set, and how did that will impact where on the MO diagram that a hybrid orbital essentially ends up, and then thinking about, okay, right, we also have then the anti-bonding combination up here, right? And then same thing here, we have the E, they're going to form a bonding combination, and then we're also going to form an anti-bonding combination. So it's pretty much the same approach that we had done for the diatomic molecular orbitals, only now instead of us being like, okay, right, an s orbital and an s orbital, we know those are going to mix, right? The 2pz and the s orbital, right, we know those are going to mix. The px and the px are going to interact, and the py and the py are going to interact. It's a lot more challenging for polyatomics to actually visualize that and come up with these combinations on your own, whereas we can just simply use group theory and the point groups to tell us what the symmetries are going to be of the different atom combinations, and then from there, right, we can think about how things work out, right? Because once we move away from hydrogen, right, we're moving away from s orbitals. It becomes much more complicated when you start having like p orbitals that are going to be doing the interacting with the central atom, right? Because you're going to have the pz, but you're also going to have the px and the py on those surrounding atoms, and that becomes much more challenging to think about how does that all work out in those cases, right? Because you can imagine, and this is a thing that once we start talking about the metal stuff will become much more the case, right? But you can have right, a system. Right, where you have all of these different orbitals right here that are all symmetrically related, but you can have one combination, right, where things are phased like this, right, but then you can have a different one, right, where things are phased like this, right, and then there's other examples and stuff like that too, where you can go through. But then the question, becomes like, okay, actually, I don't think that's the right one. It might be, but probably not, right? But this is one that I can imagine. I know for sure exists, and I know this one exists for sure too. But thinking about like, okay, well, what's the symmetry of this one? What's the symmetry of this one? Which orbitals do these interact with, or do they not have the right symmetry to interact with any of the orbitals on that central atom? Starts to become really, really tedious to do and much more time consuming than just simply going through and then determining the reducible representations of the different orbitals so that you can find out what the different possible symmetries are, and then applying those to what the symmetries are of the orbitals on that central atom, right? So in this case right here, right, I know for a fact, right, that this is going to interact with like the dxy orbital in that case, whereas this right here, right, I know is going to be a non-bonding orbital. I know that off the top of my head because I've done it a few times and stuff like that, but it's not something that's terribly obvious at first and something that you really want to think about. But it's something that through group theory and the point groups and doing the whole reducible representation thing lets us figure that out pretty easily in this case. So does that answer your question? Yep. Okay, cool. from problem 3, how do we use the MO diagram to determine the bond order using bonding, anti-bonding when there are mixed orbitals, or do we just use based off of Lewis structure? So the way that I would think about approaching it is not through the Lewis structure, right? But when we're thinking about, so just using the NH3 thing as an example, because it's a very similar problem. Right, when we're drawing out the, nope, not pen, laser pointer. Right, when we draw it out, right, we have this right here. And so one thing to think about is the fact that we know that NH3, right, has 3 single bonds. But if we're looking at this right here, we would be, we can maybe make the argument like, oh, there's actually 4 bonds, but that doesn't make any sense, right, for NH3. And so one way that you can kind of make that argument is that since this hybrid orbital, right, that one that has the mixed orbital between the sigma antibonding combination for this set right here, right, and is going to then just end up canceling out this bonding combination right here, and then you're just simply left with this combination right here as your bondings, right? So you're still able to use the same approach in those instances. So if you have, essentially a mixed orbital that has the anti-bonding combination for something that has a bonding combination already, right? That's just going to cancel that previous one out the way that you would expect it to. But then when you go then to the next step, you would expect it to cancel out the other, bonding combination, right? So in the case of the N2, the way that we can approach it, so let me just draw the N2 one, right, would be you have these guys, and so, right, we get this bond, sigma bond 1, right, we get this one, right, and so then this one right here is then the combination where you have this one is then going to be the combination of this, okay, so this is the sigma bond, so this is the sigma antibond, plus that, and then this is going to be essentially that right there, and then right, that combination right there essentially, right? So this is going to be then sigma bond, sigma bond, sigma antibond, sigma antibond, sigma bond. So you have this, 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 this. Right, and so since this right here is already that pair, right, those are going to cancel each other out, right? This is this pair, this is this pair. Those are going to then cancel each other out in that case. So that all you're left with then basically is this and then the pi bonding situation as the remainder there. But this orbital still has that character of having the 2 anti-bonding combinations in it. It's just that essentially that those combinations get canceled out, right? The bonding combinations that you had previously, but right, get canceled out by those new ones that you have up there. But you would still consider that orbital to contribute 2 electrons towards that equation to calculate what the bond orbital is. So how do you move from that point to get a numerical value, right? So right, if we think about it, right, we could always just be like, okay, right, this is a 2, 2, 2, 2, 2, 2, 2, and then 2, 2, so to say, right? So right, you have 2 electrons that are contributing to this combination, right? You have 2 electrons that are contributing to this combination, 2 that are contributing to this one, 2 that are contributing to this one, 2 that are contributing to this one. Now, even though, right, in terms of the coefficients of those orbitals, right, the easiest way to approach it and think about it, right, is that all of those are going to be canceling those different parts out in those instances. Why exactly is it that in orbital mixing, higher energy MOs move up and lower energies move down? Is there like an easy logical method behind it, or should we just accept it and memorize it? Well, I mean, the logical method behind it, right, is that in the absence of the orbital mixing, right, this one is going to be then is only going to be sigma anti-bonding, right? So it's always going to be then more destabilized. But in the presence of mixing, right, what we're now adding to it is the bonding combinations, and the bonding combinations are going to then stabilize the system, right? And so by stabilizing the system, we're going to move downwards. Similarly, right, this right here in a non-mixing case, right, would only be a completely sigma bonded one, right? And so then that one should be low in energy. But now, because we're adding two anti-bonding combinations to it, that's going to then destabilize it and then push it up in energy, right? That's the reasoning behind why the essentially the lower energy one moves even further down, and then the higher energy one moves even further up, is because the lower energy one is gaining bonding combinations, whereas the higher bonding one is now going to be, or the higher energy one is going to be now gaining anti-bonding combinations, right? So it's just going to stack on top of it and like push it even further higher up. So that's the rationale behind it. And that only happens, right, with orbital mixing. If there isn't any orbital mixing, you're not going to get that movement. Why couldn't anti-bonding sp mixing interactions contribute? So why is this not contributing to down here, is your question? Why is is this not pushing this even further down? Is that it? So why is the anti-bonding, why is this not contributing then to pushing this even further up? Is that what the question is then? Right, just the 2 sigma star and the 3 sigma. So right, so I guess thinking about it some more while I'm waiting on the whole stream to catch up, and so I'll see, right. But so I guess why is it only this one and this one that's being affected? Wait, no, sorry, just the sigma orbital, second from the bottom and fourth from the top, from the bottom. Yeah, so right, the reason that it's those two, right? So this one is going to be pushed down a little bit as well, right? Because you can kind of think like there might be a little bit of mixing that goes into there too, but more than likely not that much, just because it's going to be so far away from the p orbitals that it's not really going to affect it. Same thing for this one right here, right? That the s orbitals are going to be so far away from it that its contributions towards those orbitals, those molecular orbitals, is going to be pretty minimal, to the point where we can just neglect them for our qualitative MO diagram right here. But no, I think I get what your question is, right? Why it's only this one and this one that are being affected, and the reason for that is that essentially those are the ones that lie in between the s and the p orbital, right? And so those are going to be then the ones that have the most mixing from those orbitals with each other, in those cases, because once you start moving away from them, either above all of them or below all of them, they're going to start then having less of a contribution from the atomic orbitals that are further away, right? So the one, the first sigma orbital all the way at the bottom is going to be closest to the two s orbitals, in this case, right? So they're going to have the greatest contribution from that. The p orbitals are going to be so far away that you can pretty much neglect any kind of influence on whether or not those orbitals are pushed down or pushed up any higher. Whereas then, same thing up top with the final sigma antibonding orbital, is that those are going to be closest to the p's, and so those will be interacting more, like have more of a contribution from those p's, and those s's, because they're so far away, are going to be interacting less with them. And so, all of the antibonding character from the s-s interaction, right, is going to be sitting in between the s and the p. The sigma bonding interaction between the p and the p is going to be sitting in between the s and the p. And because the s and the p can mix in together as well, right, they're going to then be mixing in their bonding and anti-bonding combinations into those two MOs, right, that we would typically expect to happen in those cases, right? And then because of that, right, because the higher one is going to be having more of the anti-bonding character, the lower one is going to have more of the bonding character, right? And the bonding character always has to be below the anti-bonding. You can never have the anti-bonding for one interaction be below the bonding character for one interaction, right? So it always has to follow bonding, anti-bonding, no matter what. And by adding those things into it, right, by adding the bonding character, right, that pushes it down. By adding the anti-bonding character, that pushes it up, in those cases. FYI, there's like a solid 30-second delay, I think, between everything that I do and talk about here and what actually ends up on the stream. So, unless you guys have any last-minute questions, I'm probably going to end the stream so I can go to bed and be well-rested for you guys tomorrow and not mess up during lecture, if that's fine with you guys. Can you please explain how we were to exactly the place the pi body and the pi antibody? I know you briefly mentioned in class, but could we explain? Right, so as long as the pi bonding and the pi anti-bonding don't have any additional mixing, right, they're just going to end up where you would typically position them, right? So in the case of like N2, O2, F2, right, you would always just like pretty much have them at the same point. The only thing that's changing in any of those MO diagrams is actually just the position of the sigmas, so to say. Yep, you're welcome. All right, I think I'm going to call it quits. This kind of worked. Hopefully Twitch works better, because I don't like the fact that it has your guys' names in the chat, just for your guys' sake. So hopefully things will be worked out by next week for everything, and the audio and the video won't be all weird. So, all right, well, have a good night. I'll see you guys in like 13 hours or whatever.